Hello and welcome back. We have understood what is SVM and now how it works and how to apply SVM on a nonlinear dataset, and what is C hyperparameter and how it can actually make your model overfitted or underfitted by changing the values there. And then we understood the mathematical trick called as kernel trick, which actually converts your dataset into an m by m sized dataset. If you have m number of rows and n number of columns, and it will convert your data set into m by m number of m by m dimensional data set. Right? What is the advantage here? The kernel trick takes each record as a landmark and tries to measure the distance between each record and all the other records. If you see this, from this first record to first record, the distance is measured. The first record to second record, the first record to third record, like that. We take the distances and put them as values in the dataset. Ultimately, what happens? Each record is taken as a landmark. If you suppose that the columns are landmarks and rows are the original data points or data records, and then the distances between the original record and the landmark are going to be the values. So we are extracting the essence in terms of distance. If the distance formula changes, the essence changes. The kernel function is what the distance function is. So let us try to understand the RBF kernel, one of the most popular kernel function here, and then see how exactly it actually helps you extract the essence while reducing the dimensionality. I said reducing the dimensionality only when the number of records are low, the dimensionality will reduce, because ultimately the kernel trick is creating an m by m matrix. That's the key point we need to remember. Okay. So the RBF kernel function produces a distance measure between 0 and 1. When I say that, right, this distance measure is going to be a number between 0 and 1. Generally, when you use RBF kernel, to the data point and itself, the distance measure is going to be 1. At the data point and the farther data point, the distance measure is going to be 0. That helps you a lot in understanding data pattern. Okay, RBF kernel function produces a distance measure between 0 and 1. For the closest data point, it generates a number close to 1. Now suppose that the first person's DNA and the same person's DNA, you are trying to measure distance using this RBF kernel function, right? It is going to generate 1. If a good person and bad person's records, you are trying to measure the distance, it is going to generate a number close to 0. This formula generates that number. In a way, we are trying to extract the essence in between a number between 0 and 1, right? So a closest data point gets a number close to 1. The farthest data point gets a number close to 0. So RBF function is like this: e power minus of norm of x minus L square. The x is the data point, L is the landmark. For the first row, the L may be the first record, and for the second row, the L is the second record. So, in the second iteration, the L is the second record. For this third iteration, L is the third record, like that. Okay. So we'll see that with an example. So this is the formula, and the norm of x minus L square is a squared Euclidean distance between data points. Squared Euclidean distance between data points. Euclidean distance is what? Square root of x1 minus L1 square plus x2 minus L2 square plus x3 minus L2 square and so on, xn minus Ln square. That is Euclidean distance. If you apply square, right, the square root will go off. So that is the squared Euclidean distance between data points. Okay, and gamma is a free parameter. It is not standard deviation. It is a free parameter. You can play with the hyperparameter and make the model overfitted or underfitted. Along with C hyperparameter, we have got another tool or another knob to tune the model, which is gamma, sigma. Okay, sigma is a free hyperparameter. The formula, the RBF formula, is generally referred like this also: e power gamma into x minus L, norm of x minus L square. Okay. So this gamma is 1 by 2 sigma square. So in scikit-learn, the gamma is the hyperparameter. So when you increase gamma, what happens? When you decrease gamma, what happens? We'll understand. So to make the model the best, you can play with the C and gamma hyperparameters when you are using kernel SVM. Okay. So let us see how this formula calculates the distances between data points. So these are the data points, and in original data we have got x1 to x million, right, n number of DNA sequence. But after applying kernel trick, what happens? We'll take the the first data point as landmark and try to calculate distances between the first data point and the other data points and calculate the values and put it here in the cell, right? I said, right? So let us look at in the row way, right? Suppose that you have taken this first record as landmark, suppose that, okay, and you are trying to measure distance between first landmark and the first record. So between the same records, same vectors, if you try to calculate a norm, you get 0, right? The vector is 3 3 3 or 3 4 5, and you try to calculate the norm of 3 4 5 and 3 4 5, right? There is a other vector called as 3 4 5. It's going to be 3 minus 3 square plus 4 minus 4 square plus 5 minus 5 square root. So it's going to be 0, right? So e power minus 0 divided by 2 sigma square is e power 0. E power 0 is 1. So when you used RBF kernel, when two data points are very close, you got 1. Or the two landmark and data point is same, you got 1. That means if the data point and the landmark are close, right, you will get a number close to 1, maybe 0.9 or 0.99 or something like that. And for the rest of the records, for the rest of the cells, right, it's going to be from the landmark minus data point divided by 2 sigma square. So if the the value is going to be between 0 and 1, if the record is close to the first record, the genome or the DNA sequence of the second record is close to first record, then you will get a number close to 1. If it is far, you will get 0. Similarly like this. So on each of these cells, you will get a number between 0 and 1. And this matrix, the generated matrix, is going to be a symmetric matrix. See, upper triangular values and these lower triangular values are same. If you see this, the distance between RBF value between the pink person and the violet person. Here also the pink person and violet person. Violet and pink and violet. The formula is going to be same, right? So these diagonal, these triangular, upper triangular values and lower triangular values are same. So when you apply kernel trick, you will get a symmetric matrix, and you apply kernel trick onto input variables only. Y you will not touch. So ultimately what happens? A million column and 5 row data set became a 5 by 5 matrix. That's the kernel trick. Okay. So when you apply kernel trick, what happens? When you apply kernel trick, what happens? I said when a data point is close to the landmark, you will get a value which is close to 1, right? So there is a third dimension we are getting now, right? The x1 and x2 are the columns in the data set, and then you calculated the kernel function value. If you try to plot a graph between the input features and the kernel function, you will understand what is happening there. If you see this, if two data points are close, they will get the third dimension as 1. If two data points are far, the intersection, the cell value will be close to 0. So the farther, if you take one data point and try to look at whole data set, all the data points close to that data point will come close like this, move up, right? Because the RBF value is going to be close to 1. If you take all the data points which are far to that data point will go far. Similarly, all the data points which are far from one data point, maybe close to other data points, will come close, down below. It becomes easier for us to do a hyperplane or a linear decision boundary between these two types of records. The types are nothing but the classes, right? So when you apply RBF kernel or the kernel trick, it actually moves all the all the records belonging to one class to to up, and all the records belonging to another class to down, so that you will get a clean space where you can do a decision boundary. So that's how kernel trick works. Okay, so using this gamma parameter, you can actually make the model work, right? When gamma value is high, the model overfits. If you see this, all the closed data points are coming closer and closer. All the farther data points are going farther and farther. So on train set, it is trying to do that. On train set, it is trying to make it so strict that all the data points which are closer will come up, and all the farther data points will go down like that. Right? On train set, it is doing like that, but on test set and production, there is no guarantee. So you need to have some some lenience while building the model. You will give that lenience after building the model, right? When the model is working very well, and on train set test set it is not working well, then you loosen it a little bit. So you can reduce the gamma to make the model move towards underfitting, or make the model balanced on train set and test set both. I hope you are getting it. But if you look at the math here, right? If gamma is equal to 1, suppose that x minus L, the norm of x minus L square is 10. In both the cases, norm of x minus L square is 10. But when I took gamma is equal to 1, I am getting a number which is very small, 1 by 1 plus e, 1 by 1 to the power, 1 by e to the power of 100, because this is 1, right? If I took 0.5, I am getting 1 by e to the power of 50. This 1 by e to the power of 100 is very small number when compared to 1 by e to the power of 50. What happened when I said 1 by e to the power of 50 is a big number? What is happening? You are getting, even though the value is close, you are getting, you are moving the dot a little farther when compared to this one. This is very small, right? RBF value is very small. So, it's going to be kind of close. When it has to move the data point far, it is going to move it too far. This is actually close to 0. This is not that close to 0. Now what happens on the violet dots in this, right? It is going to go close to 0. If the gamma is 1, it is going to go close to 0. If gamma is 0.5, it is going to be a little up, because this 1 by 50 is going to be a big number when compared to 1 by e to the power of 100. 1 by e to the power of 50 is a little big number when compared to 1 by e to the power of 100. If you see on y-axis, 1 by e to the power of 100 is very close to 0. 1 by e to the 50 may be somewhere here. So the dots will raise a little bit. That means, it is not too strict in moving the one class data points very close and another class data points very far. So the gamma value reduces, the overfitting reduces. Gamma value increases, the overfitting increases. Same as C. When you C increase, overfitting increases. C reduces, overfitting reduces. So you can play with these two hyperparameters and make the model the best. So that is a kernel trick in theory. That RBF kernel in theory. And let us look at a code example. It's a simple one, right? I have taken the same make moons dataset, and I have taken a SVC class now, not the linear SVC, and then specified the kernel as polynomial kernel I have taken. Instead of RBF kernel, I have taken polynomial kernel. The advantage of taking polynomial kernel is, even if you raise it to 100-degree polynomial, it is going to create m by m dataset only. The problem with polynomial features in linear regression, logistic regression, or linear SVC is that the dataset dimensionality raises too much. Right? That n plus d factorial by n factorial into d factorial number of features it will create, right? But when you apply polynomial kernel in kernel SVM, it is not going to raise the dataset dimensionality. Even if you take 100-degree polynomial, it is going to create m by m dataset only, because the polynomial equation is going to be used to calculate the distance between the data point and landmarks. Right? What are landmarks? The rows only, right? The rows are the landmarks, or the persons are the landmarks. So even if you raise it to 100-degree polynomial, it's going to be okay, right? So that is the advantage of doing kernel trick, right? So if I have taken a pipeline, standard scalar, and a SVC with polynomial degree, and then here I am actually passing the hyperparameters. So SVC underscore CLF is the variable name in pipeline. To pass hyperparameter values, you need to use underscore underscore degree underscore underscore C. We know that C is used to handle overfitting and underfitting, and coef0 is a hyperparameter which actually handles the shrinkage. It is like shrinkage parameter, alpha in our linear regression and logistic regression, shrinkage parameter, right? So C is one kind of hyperparameter, and this coef0 is another kind of hyper. So all these three are trying to handle overfitting and underfitting. Okay. So I have taken grid set CV and I passed 39 values. So it's going to do 9 into 9 into 9 number of models. So degree, it will take 1 from 1 to 9. The C, it will take 1 to 9, and coef0 also it will take 1 to 9, and it is going to take 1 1 1 build a model, 1 2 1 it's going to build a model, 1 2 2 it's going to build a model, 1 3 1 1 3 2 1 3 3, like that it is going to pass values to the algorithm and build models and see which one is working good. If 1 1 3 is working good, right, it is going to say that degree 1, C1 and coef3 is the best model. So that's how the grid set CV works. Okay, so I passed the polynomial the pipeline, and then the param grid, and did the grid set CV, and it found the C value 1, coef9 and degree 4 worked well. And if you look at the decision boundary, right, it is so neat. So that's how you can do kernel SVM. If you don't specify any kernel, it's by default it's going to use RBF kernel, radial bias function. Okay, the one we have understood. Okay, so that is the kernel SVM, and thank you.